Alrighty, our fourth homework assignment from this unit on solving quadratic equations. Question 1 says if the equation x plus 10 times x equals 0 is true, which statement is also true according to the zero product property? Well, that means that each one of my factors would have to be able to equal 0, which means I have x plus 10 equals 0, or I have my other factor of x equaling 0. So let's see here, that is B. I know that I have two options. It's when x equals 0 or when x plus 10 is equal to 0. All right. 2. What are the solutions to the equation 10 minus x times the quantity 3x minus 9 is equal to 0? So I need to set each one of my little factors equal to 0. So I'm going to ask myself, when is 10 minus x equal to 0? Well, if I add x to both sides, I end up getting x is equal to 10. So there's my one solution. And the other one, I need to ask myself, when is 3x minus 9 equal to 0? Well, if I add 9 to both sides, I get 3x is equal to 9. Divide both sides by 3, I get x is equal to 3. So there's my solutions, 10 and 3, which puts me at C. 3 says solve each equation. It's already given in factored form. I'm hoping we can start to see how quickly and easily this can get done. Most of these, if it's just one number on the inside, you should be able to tell what it is right away. So like for example, A, you should be able to tell that your solutions are 6 and negative 5 by now. Just glancing at it, you can tell that when you plug in 6, you get out 0. When you plug in negative 5, you get out 0. B, it's the same thing for the one solution of 3. The one you might have to do a little bit of thinking about and redoing or solving for would be asking yourself about that factor, the 2/3 x minus 6. I'm going to ask myself, when is 2/3 x minus 6 equal to 0? That is a two-step linear equation. Add 6 to both sides. I get 2/3 x is equal to 6. And then multiply both sides by 3 halves. I could make it 2. That'd be helpful. 3 halves. And if I'm multiplying by 3 halves, I get x is equal to, let's see here, 6 divided by 2 is 3. 3 times 3 is 9. So my other solution is x equals 9. And then it'd be the same thing for C. The factor x plus 7 produces the solution negative 7. That's very easy to see. But you might have to do just a little bit of thinking for the negative 3x minus 15 and ask yourself when that's equal to 0. Two-step equation, add 15 to both sides, you get negative 3x is equal to 15. Divide both sides by negative 3, you get x is equal to negative 5. So again, just building on what we've already done in the past, and we should get to the point where we can solve linear equations very, very rapidly. 4 says consider the expression the quantity x minus 4 times the quantity 3x minus 6 and the expression 3x squared minus 18x plus 24. Show that the two expressions define the same function. Well, there's a lot of ways I can do this. One way is by looking at them graphically and putting them both in y equals, but the way easier way is just to multiply these two binomials together, those two factors together. And if I were to do that and put it in standard form, they should match up. So let's do that. X times 3x is 3x squared. X times negative 6 is negative 6x. Negative 4 times 3x is negative 12x. Negative 4 times negative 6 is positive 24. Collect like terms, I get 3x squared minus 18x plus 24. And that is exactly what we were given. So I know that they define the same function because they are equivalent expressions. Question 5 says Kieran saw the equation x plus 2, the quantity x plus 2 times the quantity x minus 4 is true. Then by the zero product property, either x plus 2 is 0 or x minus 4 is 0. He then reasoned that if x plus 2 times x minus 4 is equal to 72 is true, then either x plus 2 is equal to 72 or x minus 4 is equal to 72. Explain why Kieran's conclusion is incorrect. Well, the reason why 0 is so special is the only way to multiply it together to get to 0 is if one factor is 0. Well, that's not true about 72 because there's a crazy amount of ways to multiply to 72. Many ways to multiply to 72. So really that's it in a nutshell. The reason why Kieran's conclusion is incorrect is because there are multiple ways to multiply to 72. And really, when he says x minus 4 is equal to 72 and x plus 2 is equal to 72, we're really only taking consideration one of the tiny, many possibilities that it could be. 6, Andre wants to solve the equation 5x squared minus 4x minus 18 equals 20. He used a graphing calculator to graph y is equal to 5x squared minus 4x minus 18 and y equals 20. It finds that the graphs cross to the points negative 2.39, 20 and 3.19, 20. Substitute each value, x value Andre found in the expression, and then evaluate the expression. So I'm just going to plug those numbers in, and instead of, it's going to take a while to plug it in the calculator, so I'm just going to do it and tell you what I get out. So if I evaluate that expression, if I take 5 times negative 2.39 squared minus 4 times negative 2.39 minus 18, I actually end up getting out 20.1205. And if I were to do that with my other number, the other quote-unquote solution, I would get 5 times 3.19 squared minus 4 times 3.19 minus 18, and I end up getting out 20.1205. They are very close, but they're not exact. Why did neither solution make 5x squared minus 4x minus 18 equal exactly 20? Well, because our solutions are approximations. More than likely, these solutions are actually irrational numbers that we are going to have to learn how to find exact answers for later in this unit. 7 says select all the solutions to the equation 7x squared minus, 7x squared equals 343. So if I were to try to solve this equation, I would divide both sides by 7, and I would get x squared is equal to 49. And I would solve by taking the square root of both sides. And as I do that, I know that the square root of both sides would produce a positive and a negative version of 7. So really, I'm looking for all the expressions, all the numbers here that are equivalent to 7 or to negative 7, because I know those are my solutions. Clearly not A, clearly not B, because negative of the square root of 7 is far different than the actual negative of square root of 7, or the negative of 7. C works, D works. The square root of 49 is the same thing as 7, that works. The square root of negative 49, I can't actually do. I can't take the square root of a negative number. This is broken. We will learn about this before the end of the unit. This is an imaginary number, but we don't know how to do that yet. And then negative of the square root of 49 is the same thing as negative 7. So that one works as well. Question 8. Here are 2 graphs that correspond to 2 patients, A and B. Each graph shows the amount of insulin in micrograms in a patient's body 8 hours after receiving an injection. The amount of insulin in each patient decreases exponentially. Select all statements that are true about the insulin level of the 2 patients. And I could do this a whole bunch of different ways. So I could start identifying some key characteristics before I start looking through all the answers. But because I'm going to treat all these basically like true false, I think it's going to make more sense just to read each one and kind of ask if it works or not. So let's go ahead and read through these. A says after the injection, the patients have the same amount of insulin in their bodies. Well, that would be meaning at t equals 0, the y-intercept or the vertical intercept. So I'm looking here, patient A looks like 200 units or micrograms of insulin at time 0, whereas patient B has a lot more, has 320. So after the injection, the patients do not have the same amount of insulin, which means, nope, not A. B says an equation for the micrograms of insulin for A in patient A's body 8 hours after the injection is A is equal to 200 times 3/5 H. Well, I know right away that the 200 makes sense because I already have my y-intercept at 200. The only other thing I need to check is that base of the exponential. In order for me to do that, I need to figure out what that multiplier is. So I need to identify one more point. I'm going to identify this point right here. It looks like I have the point 120. So I need to ask myself, what do I have to multiply 200 by to get to 120? Because that is that common multiplier, that is that base. I divide both sides by 200. I end up getting x is equal to, let's see here, that's 12 over 20, which simplifies to 6 over 10, which simplifies to 3 over 5. And look at that, that matches up. So through a little bit of work, I can tell that the base of that exponential is 3/5, which means that is going to match into that graph. C says the insulin of patient A is decaying at a faster rate than the patient B. Well, I know that in A I'm multiplying by 3/5. I should figure out what I'm multiplying by in patient B to see which one is steeper, which one is losing more quicker. So I'm going to do the same exact process over here for patient B. I have another point here at 20, 40, 60, at 160. And I can tell very quickly that the decay factor here, or the base, the number I'm multiplying by, is going to be 1/2. Because if I think about this, I know that 320 times some number is going to get me to 160, and that number is going to be 1/2. So the question says the insulin patient A is decaying at a faster rate. Well, here, if my decay, or if my multiplier is 3/5, I'm losing 2/5 every hour. So my decay rate is, I'm going down 2/5 every hour. With patient B, I'm going down 1/2 every hour. So with that being said, I know that patient A is not decaying faster. He's actually just decaying a little bit slower. I can tell by looking at the bases of those exponentials. I can also tell because the steepness of the graphs, patient A's graph is less steep. D says after 3 hours, patient A has more insulin in their body than patient B. Well, this is going to be kind of tricky here because if I were just look at the graph, they look like they're right about in the same spot. But I've already gone through and I have an equation for patient A. And really, I have enough information between the base of the exponential and the y-intercept that I should be able to write an equation for patient B as well. So I'm actually going to plug in t equals 3 into those two equations I come up with. So patient A, we already know that A is equal to 200 times 3/5 raised to the h power. And patient B, we started at 320. Helpful if I could write. Patient B started at 320 and I was multiplying by 1/2. So the question becomes, if I plug in 3 there, which one's going to be bigger? So if that's the case, patient A, I would have 200 times 3/5 raised to the 3rd power, which if I plug that into my calculator, I get 43.2. Patient B, if I were to take and plug in that 3, I would get 320 times 1/2 raised to the 3rd power, which I would get out 40. So in this case, it looks like after 3 hours, patient A has more insulin. So let's see how we answer the question. It says after 3, patient A has more insulin in the body than patient B. That definitely checks out. So I need to circle D as well. At some time between 2 and 3 hours, the patients have the same insulin level. I can do this just by quickly glancing at the graph. Between 2 and 3, so that means I'm pinching between these two places, and I'm pinching between these two places, and it definitely looks like they are right in there where they're going to be crossing. If I want to take this even a step further, I've already written the equations for the exponentials, so I could just default to using my calculator for a second, and I'm going to go ahead and type in the two equations I had. I had 200 times 3/5 raised to the h power, but we're going to just use the variable x here. And then my other one was 320 times 1/2 raised to the x power. And I'm going to mirror the window we have on these graphs. So window from 0 to 6, and from 0 to, I don't know, about 400 it looks like. Oops, it would help if I put it in the right spot. 0 to 400. So that's essentially what we're looking at here on our actual worksheet, or on the actual, what we're given. And if I'm looking for where they cross, I can tell they're going to cross somewhere between 2 and 3, specifically right there. So I can go ahead and circle that last one as well. All right. Question 9 says, Hans says this pattern of dots can be represented by a quadratic relationship because the dots are arranged in a rectangle in each step. Do you explain, or do you agree? Explain your reasoning. Well, there's a couple different ways of doing this, but the first thing I'm going to do is I'm just going to identify how many dots are in each to see if I can't see the pattern. If that's the case, I'm just going to count. I have 4 dots in step 1. Let's see here. I have 8 dots in step 2, 12 in step 3, and 16 in step 4. So I can tell that this, even though I have a square, I'm constantly just adding 4, which means this is not quadratic in nature, this is linear in nature. So do you agree? No, this is actually linear. Linear with a constant rate of change of 4. And that's the last question for this homework assignment. That was our 4th lesson on the unit on solving quadratic equations.